In this session, we're going to thoroughly discuss the Granger Causality function, and as is our standard procedure, we will be utilizing our dedicated website to effectively perform this particular function.
However, before we dive into the specifics, let's take a moment to establish some foundational theoretical context. So, the concept of Granger causality can often be quite misleading in its naming. Pause, because its core focus isn't truly on, the underlying economic or structural causes. Pause, that's simply not what it's designed to measure. Pause, what it truly concerns itself with is the ability to predict. So when we talk about Granger causality, we're really focusing on the flow of information as it unfolds across different points in time. It's important to understand that this concept is quite distinct from structural causality, which delves much deeper into identifying and investigating the actual underlying mechanisms of influence at play. So, in this particular scenario, our focus is not on examining the direct causal influence of the x variable upon the y variable. Instead, what we are truly aiming to investigate is whether a discernible pattern of predictability exists flowing from the x variable towards the y variable. So the principle of Granger causality essentially poses the following question. After we have controlled for the previous values of y, does the past value of x still provide any additional help in predicting y? This phenomenon is precisely what we refer to as Granger causality. And pause. Our primary objective here is to meticulously examine and determine if the inclusion of an additional x variable within our analytical framework can substantially contribute to enhancing the overall forecasting predictability of the y variable. So, in this context, we're actually working with two distinct sets of equations. The initial one, which we refer to as the restricted model, is specifically designed to operate as a function solely dependent on the previous values of y, serving as its regressors.
The unrestricted model, where we also include the lagged value of the variable x, which means that we now have a greater number of regressors.
So, what we're looking at here is essentially the full, or you could say the unrestricted form of the equation. This is because it incorporates not just the past or lagged value of the specific variable we are trying to forecast or predict, but it also includes the independent x variable.
So we have more regressors in this case.
Does this particular set of information, specifically these types of regressors, actually provide a more accurate forecast compared to the restricted model in which we exclusively utilize just the lagged value of the y variable for our forecasting purposes, which is precisely what we see here? If this is indeed the case, then we would typically express this by saying that x is Granger causal, or to be more precise, we would state that there is Granger causality running directly from the x variable to the y variable. Another common way to phrase this is simply that x Granger causes y. In this specific situation, the historical data of variable x offers highly valuable time-ordered insights crucial for predicting variable y. And once again, it's absolutely essential to underscore that this does not imply that if we were to modify a specific x variable, then the outcome y would automatically shift as a direct consequence of that intervention. Because our discussion here is not about the deeper structural causality of things, but instead it's focused on the predictive forecasting capability. So, for example, let's consider a scenario where x represents a variable that consistently responds a little bit sooner than y when new information arrives. In such a case, it's plausible that x could effectively predict the behavior of y. It's entirely possible that both variables might actually be endogenous, meaning they could be responding or reacting to a single, more profound underlying force. For example, let's consider two distinct stocks operating within the same industry. However, it's quite clear that one of these particular stocks receives significantly more attention and coverage from a larger number of financial analysts than the other investment option. In this particular scenario, we are observing significantly enhanced capabilities for processing market-relevant information. This leads to a much more rapid and immediate reflection of all pertinent data directly into the current stock price. Consequently, this specific equity will inevitably exhibit a considerably swifter and more pronounced reaction when compared to other available stocks. In this specific scenario, we can effectively utilize the price action of that particular stock, which is more closely observed by market analysts, to accurately predict the future movement of the other stock. That doesn't necessarily imply that the specific stock we are currently using to predict that the movements of one particular stock are the sole cause of the shifts in the valuation of another, but instead it more accurately reflects the fact that this stock simply responds to new market information at a much quicker rate.
This is a very good example of the Granger causality.
So, the restricted model, as we have previously explained, was one where we are simply using the lagged values of the y variables, and only those. You can use lag 1, extending all the way up to lag p. The unrestricted model, however, will utilize the same lag components, but additionally we are going to incorporate the x variable itself into the model. This is precisely why we observe terms such as xt-1 and xt-2 within our framework. We can continue to add these terms progressively until we eventually reach the specific point of xt minus p. The null hypothesis for Granger causality is that we don't have any significant causal influence. An incremental forecasting power from adding these variables, meaning that the coefficient collectively is equal to 0. So if statistically all of these coefficients are not found to be significantly different from 0, then their inclusion does not improve the model's predictive ability. Are equal to 0, then we would reject, actually we cannot reject the null hypothesis under those circumstances. However, should we observe that at least one of these particular coefficients proves to be statistically significant and distinct from 0, this would then clearly signify a very important conclusion. It means that we indeed possess the capability to establish Granger causality, running from the x variable to the y. However, if we observe that even a single lagged value of x possesses the capacity to forecast the future behavior of y, then this finding implies that we are able to confidently reject the established null hypothesis. And we can confidently state that there is a significant Granger causality impact, and as a result, we must accept the null hypothesis, because one of these particular lag variables to possess a coefficient that is statistically different from the null hypothesis of 0. So what we're discussing here today is primarily focused on the concept of Granger causality. To illustrate this point, let's consider a straightforward example involving our y variable and the x variable. If our goal is to understand the underlying mathematical operations, we can simply trace the numerical calculations presented right here. So the very first thing that we must do is to construct the restricted model. For this, we will need to incorporate the lag of y. And also we can have a potential explanatory variable. The core idea here is that we need to perform two distinct regression analyses. After running these, our main task is to carefully compare the resulting sum of the squared errors from each. So for the first regression, we model the variable y based on its own previous value, or its lag. This specific setup is what we call the restricted model, and we're setting it up right now. We're going to be using this matrix algebra. And we have already explained this in detail in many other videos. So for the initial step of estimating the coefficient, we need to calculate the product of x with itself. This operation will then yield a matrix, specifically a symmetric matrix. The very first element within this matrix represents the total number of observations. In our specific example, we actually have 7 observations. The second element is simply calculated as the sum of the x variable. In this specific instance, the x variable is actually the log of y. This is because we began our analysis with the restricted model. Therefore, that would represent our x value within this specific equation. And regarding the final component, it's quite straightforward. If we take the regressor, square its value, and then proceed to sum all of these resulting figures together, we will ultimately arrive at this specific numerical outcome. Now, the other part we need to consider is directly related to our y variable. This involves the sum of y itself and then the product of the regressor and that same y variable. So essentially, we have these two distinct elements, and then we simply multiply this matrix by the other one to obtain our final answer.
So notice that when you're doing multiplication,
so this specific component here will provide you with a constant term, and then that one will determine the coefficient of the regressor.
and when you're carrying that out,
Then from this we can obtain the following coefficients, specifically alpha. And also, of course, for beta. So the alpha represents a constant term, and this here is beta, which is the coefficient attached to our regressor. Now, in this particular case, for the restricted equation, it's simply the lag of y. That's because the lag of y in this context is treated as a regressor, essentially an x variable. Now, the second phase requires us to execute the operation. And then we need to calculate the sum of the squares of the residuals. These residuals represent the actual error that arises from estimating the equation. We need to assess how accurately this equation truly fits the actual observed data. In this specific scenario, we simply substitute the actual lag value, or indeed the actual values of the regressor variables, into the equation to obtain the predicted outcome, which we call y hat. Subsequently, we then compare this predicted value to the actual observed value.
Therefore, through that process, we can accurately determine the specific error corresponding to every single observation.
After finding the errors, we then calculate the square of each,
and then add them all up together. That will then give you the total sum of the squared residuals. If we have large residuals, it truly doesn't matter whether that error is in a positive direction or a negative direction. This is because at the end of the day, we square those values. Consequently, the larger the deviation from the fitted line, as predicted from our statistical equation, if the actual observed values deviate from that line or from the predicted value, then we will certainly have a very large sum of the squared residuals. And that indicates a less satisfactory equation. Consequently, we have arrived at a particular figure, specifically 23. The fundamental concept at this juncture is that we must proceed to compare this particular value against the results derived from the unrestricted regression model. Now, if we were to incorporate an additional regressor into our model, it inherently leads to an improvement in its predictive capabilities. This means that our predicted y value will inevitably move much closer to the true actual observation, and as a direct consequence, the overall error term will naturally be reduced. But our primary objective is to ascertain if the observed enhancement, or more precisely, the reduction in the overall error term, which is quantified by the sum of the squares of the residuals, demonstrates a statistically significant decrease when we are utilizing the unrestricted regression approach.
So, we're going to perform the same operation, which involves finding the coefficient for the constant beta and the coefficient for the new regressor. We apply the same equation. The idea is quite similar. We're looking at two distinct parts, the product of x multiplied by itself. As a result, we're obtaining a 3 by 3 matrix. It's noticeably larger because we now have two regressors involved. So that element, for example, is the sum of y's lag, called x1.
This particular value we're looking at here represents the sum of our second regressor, which, as you can see, is clearly designated as x, specifically this one right here. And then moving on, that would be the sum of the squared values for our first regressor, x1, which is this specific variable we're currently examining, and that will be... First, we need to determine the product of our two important variables, x1 and x2. So once we have successfully obtained this resulting matrix, we then proceed to invert it. After that crucial step, our next action will be to multiply it by... Let's look at this particular element, which is x multiplied by y. This calculation should then provide you with the overall sum of y as an example. Here we have the product of x1 and y, and separately the product of x2 and y. Finally, you will take these two distinct parts and multiply them together.
And then, after all those calculations, we finally arrive at the ultimate coefficients. Now, if we were to consider...
We must substitute the actual values of the regressor into the model to obtain the fitted value or the predicted value of y.
Does the predicted value get closer to the actual value, which would mean that we achieve a lower number of errors?
Therefore, in this specific scenario, we must determine the total sum of the squared residuals.
We are carrying out that particular task right here. Then we take the error and square its value, and then we proceed to sum all of them together.
Therefore, the sum of the squared residuals from the unrestricted model, meaning the model where we included an additional regressor, is 0.8.
So we calculated the error, squared it, and then we added that result, which ultimately gave us this number. So at that point, we really must compare the restricted version with the unrestricted one. Visually speaking, they present themselves as being quite different and also significantly lower. So by incorporating just one more additional regressor into our model, we observed a truly significant reduction in the sum of the squared errors. It dramatically decreased from an initial value of 23 all the way down to a mere 0.8. This is an absolutely massive improvement achieved simply by introducing that single extra regressor. So the Q that we're discussing here is simply the number of additional regressors that have been included in the unrestricted model. Then we calculate a specific ratio, and that particular ratio is what we refer to as the F statistics. So we are comparing the sum of squared residuals, which by default should be higher than the unrestricted one, However, what we are doing is comparing that particular reduction, and we're doing so by considering the total amount of the sum of the squared values of the residuals that come from the unrestricted model.
So what we have here is an improvement. As we've previously stated, it's quite significant. Because the initial value was approximately 23, but now in this particular instance, it has dropped significantly to just 0.8, and this remarkable substantial difference, this huge change was achieved solely through the influence of a single solitary regressor.
So when you divide by 1, that large value will remain, rather than if you were to add, for example, 2 or 3, that would be divided into a much smaller amount. And then you compare it to the total sum of the squared residuals, which is quite low, relatively speaking, particularly when you consider the total number of observations.
So if the number of observations could be 10 or 7, minus the parameters estimated in the unrestricted model, which is 3. And it once again represents the regression sample size. It was not what you would call a particularly large number. In fact, it was something like nearly 7 or perhaps even 9.
So when you substitute these numerical values into the equation, you will then be able to observe the degree of relative improvement that has been achieved within the statistical model that was fitted, or the corresponding reduction in the sum of the squared differences between the observed and predicted values.
Should that observed reduction prove to be statistically significant, then the resulting F statistic will consequently increase in magnitude, and this outcome would likely lead us to reject the established null hypothesis, which posits that the newly introduced independent variable, denoted as x,
it's not statistically significant. This represents the null hypothesis, specifically because the coefficient we're looking at, gamma,
according to the null hypothesis, the coefficient associated with this new regressor is considered to be precisely 0, which implies that the inclusion of this particular new regressor within the unrestricted model will not significantly enhance its ability to forecast or predict the variable y.
On the other hand, if the calculated F value is sufficiently large, then we are able to confidently reject this null hypothesis and conclude that no, the addition of variable x will significantly enhance our ability to forecast the y variable.
When we carry out the statistical calculation for this specific example, we observe that the F value is exceptionally large, reaching 108. This allows us to confidently reject the null hypothesis, which states that adding an additional regressor does not significantly improve the overall predictability of the model. We are able to reject this, and we can confidently state that the inclusion of this specific regressor is capable of significantly enhancing the predictive power, which ultimately signifies that this particular variable does indeed Granger cause the dependent y variable. So, the ultimate and definitive conclusion we've reached is that X Granger is indeed the cause of Y. So let's begin to put that into practice now using the website. I'm going to choose the specific time series data.
First, we'll set this to monthly. Then I'll proceed to select the start year as 2000 and the end year as 2024 before we finally apply these changes.
The main variable that we are specifically interested in predicting as part of this model is going to be the monthly stock return for Microsoft. This specific value, the monthly stock return, will be designated as our primary Y variable. So in this particular instance, we will then proceed to scroll down and search for this specific variable.
And then for the purpose of this demonstration, we will be measuring that data exclusively for a single firm. Therefore, our next step involves searching for the Microsoft stock ticker symbol, which is commonly known as MSEFT. First, we'll click the Enter key, and then we'll click somewhere outside of that. We need to give it just a little bit of time to process. And then right here in this specific box, we are going to see our search ticker appear. At long last, we're ready to announce the official name change. It will now be M, a true Microsoft return. And then we'll just go ahead and click. Okay, we're finally finished with this part. We've successfully determined the monthly stock return for Microsoft, which is of course our primary Y variable.
Now, in the restricted model, let's start with the restricted model. In that particular scenario, the lagged return of Microsoft is considered to be the sole and exclusive regressor.
Now, within the context of our unrestricted model, we are going to incorporate just one additional regressor, and that will be the overall market return.
I'm picking median.
Now we need to find the market return, and we'll use the median monthly return across firms in each month.
At this point, our intention is to apply this policy to all firms. Consequently, we will leave these specific fields empty. We are not going to limit our comprehensive search to a particular subset of companies, but instead, we will ensure it applies universally to all firms.
However, because we are specifically dealing with time series data, we absolutely need to find an effective way to summarize all these numerical values across every single firm for each month into one single representative number.
So, you essentially have two main alternatives here, the mean and the median. I personally prefer to use the median because it is less exposed to outliers.
Then we click apply.
Now,
We have the
Changeable.
It's important that we rename this particular item, and its new official designation will be the market return. To ensure this modification is properly applied, simply click your mouse cursor anywhere outside the current input box, and the change will then be fully enacted.
We now possess our primary dependent variable, y, and our key independent variable, x.
We can plot them here to visualize the market's current state. And we're specifically looking at the monthly financial performance of Microsoft's stock. Here we have the market with all its complexities, and then, of course, there's Microsoft.
It appears that these entities are generally trending in a similar manner, which, when observed over time, is quite predictable. This is primarily because, as we understand, significant market disruptions will inevitably impact the firm, leading them to consistently move in the same general direction. Given this, can we effectively use the broader market's overall return to accurately predict Microsoft's specific monthly performance? In this case, to answer this question, we'll need to employ the Granger Causality method. If you navigate down to the low air section, and more specifically to the final box presented here, which deals with causality, you will then discover the Granger test. So, as you can see, we're dealing with a variety of different tests here. The first of these, which we examined in detail with a clear numerical example, is indeed the pairwise test. That's the one, isn't it? Therefore, that's the option we should proceed to select.
And the primary independent variable that we are specifically interested in evaluating and testing here is
Market return.
Now, in this particular instance, we won't be explicitly adding the lagged value of y as an independent variable, or x. This is because, by default settings, the application itself is designed to automatically identify the restricted model. It achieves this by taking the lagged value of the Microsoft return and then treating that specific value as a regressor in its calculations.
First, you'll need to perform the regression analysis, then record the resulting coefficients. Next, calculate the prediction errors and carefully square each of these individual errors. Finally, sum them all up to determine the SSR, which is the sum of the squared residuals.
The application will take care of that automatically. What you're required to define in this particular context is your chosen predictor, which in this specific instance is the market return, and we did. Our primary objective is to make a return to Microsoft.
Here you specify how many lags you want, like how many lags of X you'd like to include.
I am quite confident that a single lag period will be entirely sufficient for our current investigation.
Consequently, the crucial question is whether the preceding lag of the market return can truly Granger cause or accurately predict the subsequent returns of Microsoft.
Furthermore, we have the capability to test the inverse, which means considering a scenario where we utilize y as x and then conversely x as y, completely flipping the entire situation. This particular functionality could easily be implemented as an option right here.
There's no need for us to make any adjustments to the endogenous component because this is not related to the pairwise normal Granger causality. I believe that we're now completely prepared. We can simply proceed to execute the process.
And most likely we're not going to have a relationship, because if we do, then it would become quite an effortless task to generate significant profits simply by observing the market's financial returns from the previous month. And if we were able to accurately and significantly predict the future movement of Microsoft or any other particular stock, then engaging in market trading would become incredibly straightforward. The market simply doesn't function in that way due to the presence of random walks and the concept of market efficiency. Consequently, these factors are indeed correlated, as we clearly observed in the graph presented earlier. However, it does seem that this specific occurrence took place within the very same calendar month. So within that identical month, we consistently observe them moving in a specific direction. The principle of Granger causality, in its simplest form, is merely about utilizing the historical data of X to make accurate predictions about Y's future behavior.
Under these specific circumstances, if the financial market is truly efficient and all relevant information is rapidly incorporated into stock valuations, whether for individual stocks or the entire market, then you would certainly expect to see a highly synchronous movement.
Well, however, the actual power of predictability might not really exist. In this particular case, if you take a look at the statistic right here,
if you were to conduct a test to see if the broader market's return can Granger cause the stock performance of Microsoft, specifically when we consider a lag of just one period, you'll find that it is not statistically significant, because the p-value that we observe here for the F statistic that we calculated, that we mentioned earlier, specifically this one right here, the p-value, not the F statistics we might be looking at. The statistical power of this particular result is actually quite weak because the p-value is significantly larger than the standard 5%.
The observed value is remarkably high, specifically registering at 0.71. Consequently, we must reject the hypothesis of pairwise Granger causality running from X to Y. Furthermore, the reverse relationship also does not hold true.
Microsoft is not able to accurately predict the market's future returns, so that idea can also be dismissed.
Now, regarding the other available options here, we could potentially use, for instance, a more complex Granger causality version, specifically one that includes the block VAR model. In this particular case, we are dealing with a system of equations.
So, for the block VAR model, in this instance, we are plotting two separate equations, not just a single one. This means our Y variable contains the lag component, the restricted component, and also the additional component. And this entire setup represents what we call the unrestricted model.
but we also consider X to be a Y variable, meaning it's also dependent. So in this particular model, we actually have two endogenous variables, that is both Y and X. Consequently, the variable Y can be influenced by its own past values and also by the previous values of X.
Also, we have another equation where the X is affected by the lag of the other variable, in this case the lag of Y and the lag of itself. So here, instead of having one restricted or unrestricted equation, we have two.
And this is precisely the reason why we have the VR system of equations.
And essentially, our objective is to determine if these coefficients, given our primary interest in predicting the variable Y, are significantly and jointly different from zero. If these values are different from zero, then we can say there is a Granger causality running directly from X to Y. However, the crucial point here is that we are performing this analysis while controlling for the other regression. Here we have a quick, straightforward numerical example that illustrates the coefficients. And this is precisely the method we utilize to test for Granger causality, particularly when we're dealing with a vector autoregressive or VAR system.
We are going to be making use of what is referred to as the Wald statistics.
The Wald statistic essentially serves to determine whether these particular coefficients are significantly distinct from a value of 0. Pause. Therefore, if there's a noticeable discrepancy, meaning they are indeed different and sufficiently distant from 0, we then proceed to square that observed difference. So we first identify the gap, and then we also account for the inherent uncertainty of that particular gap. Or, for example, if the raw gap value is quite high and the associated uncertainty of that gap is relatively low, then we will certainly observe high and statistically significant Wald statistics. So the Wald statistic we're examining here is essentially the gap squared, which has been adjusted to account for uncertainty. And if you follow this numerical example, that represents the uncertainty associated with the coefficient. For instance, this value is the variance or the uncertainty of the coefficient for xt minus 1, which is indicated here.
And the uncertainty of this particular coefficient,
the necessary information is clearly presented to us right here, and if we meticulously follow the steps of this mathematical framework, then we are absolutely going to uncover a wealth of significant statistical findings. Furthermore, it's worth considering that we possess the capability to implement the Toda Yamamoto augmented vector autoregression model as a distinct and equally valid alternative option. In this particular case, the primary motivation would be if we have variables which are not stationary. We typically find that this causes a significant problem in the field of econometrics. Therefore, if we are dealing with non-stationary variables, then this technique becomes quite useful. So, this specific technique will not apply differencing to the variables in order to make them stationary. Therefore, this approach will completely avoid using the differencing methodology. Instead, it will maintain the original level form of the data, ensuring we don't lose any valuable information.
However, this action will inevitably introduce a noticeable amount of additional delay.
So the way the Toda Yamamoto method operates is by ensuring that the variable remains non-stationary.
So, the standard word assessment remains perfectly valid for use, and it has been thoroughly confirmed that it does not exhibit any form of bias.
So, for example, the usual chi-square distribution, which, as you know, relies on regular asymptotic conditions. And if you're dealing with a non-stationary process, then this will create some residual persistence in the data, which can then contaminate the validity of our test statistics.
To prevent potential issues that might arise and to ensure that all our variables are maintained in their original undifferenced level form, we typically introduce one additional lag. However, if we encounter a significantly high degree of non-stationarity within the data, it becomes necessary to incorporate even more lags into our model. So the D here actually refers to the stationarity level. For example, if D is set to 1, it signifies that you would need to compute the first difference of the specific variable in question, which is essential to transform it from a non-stationary series into a truly stationary one. 2. This implies that you'll need to apply differencing operations, perhaps even a second difference to achieve stationary data. 3. And the pattern continues for higher orders. If you detect a single unit root, it means you'll need to incorporate one additional lag term as a regressor, or for every single regressor already present in your model equation. This specific statistical procedure is what we refer to as the Toda Yamamoto test. For example, if, in the original setup, you are utilizing 2 lags of the regressor variable for this particular analysis, considering both the restricted model and, of course, the unrestricted model, our focal variable of primary interest.
the variable that we want to add and then test whether it Granger causes the y. If the original number of lags is set to 2, the method employed will automatically incorporate an additional lag,
And that one more problem will be here.
this is the additional lag, and this is the additional lag for the other regressor.
And we can certainly accomplish that right here. It's important to remember that whenever you're utilizing the VAR model, you absolutely must ensure that you select both variables as endogenous.
We can also make use of the
VECM, which is the vector error correction model, is specifically designed to effectively control for the long-run relationship between variables.
For example, if you have 2 non-stationary variables, they can become stationary if we simply take their first difference. However, it's also possible for them to be cointegrated, and we've already covered cointegration in a separate video.
Cointegration essentially means that when you have two variables, y and x, which are individually non-stationary, the specific long-term relationship can in fact be stationary. This stable long-run connection is the essence of cointegration.
So if you take yt subtracting a certain coefficient multiplied by xt, that difference can be stationary over time, meaning they share a long-term relationship.
In this situation, when we are applying the VECM within the context of Granger causalities, it's crucial that we first compute the first difference.
Or the final difference, depending on the specific number here. Or the final difference, depending on the specific number here.
So what we do is we first transform all of these variables to make sure they become stationary. And then in addition to that, we're also going to incorporate their long-term or long-run relationship term. This particular term is what we call the error correction term. The main difference we're focusing on here is quite simply that error correction.
So, for instance, if the y variable deviates significantly from its established equilibrium point, which we're referring to as this particular one here, then it becomes necessary to introduce specific adjustment or correction values to bring it back into alignment.
For example, let's consider a situation where the variable y is currently observed to be significantly larger than its established long-term equilibrium relationship. In such a case, it would be reasonable for us to anticipate a necessary adjustment in the system. Consequently, we would then expect the value of yt to decrease and move downwards during the subsequent time period.
So this will become a truly significant element within our forecasting process because we can accurately predict the movement of y, assuming we possess the error correction term.
So, what we're doing here is capturing the normal short-term predictive capability that we've been discussing right from the very beginning, which relates to the Granger Causality concept.
We have the unrestricted factor, which is essentially the same y variable from a previous time period or lagged. Then there's our primary variable of interest, which serves as our main regressor in the model.
Also, we'll capture the long-run adjustment toward equilibrium.
And this is something we can definitely achieve right here. Your only task is to make one minor adjustment. All other elements must remain exactly as they are.
And then you start running. And you obtain the findings. It's like the integration order.
As we previously mentioned, one example is quite typical.
The cointegration rank value. And you might be considering whether you need to apply a differencing operation here. In that case, a single first difference will actually be quite sufficient, provided you have cointegration at the first level. So, once these analyses are completed, we then compile all the key findings into this document, and what we've discovered is the following, specifically the pairwise analysis, which was something we talked about right at the start.
We don't have any significant relationship, and we mentioned that before. When analyzing the block VAR system, we still haven't identified any statistically significant relationship, whether we examine the first lag or the second lag.
For the other equation, the result is precisely the same. Therefore, we find no significant Granger causality present within this VAR system. There is absolutely no statistical evidence. No evidence to indicate that Microsoft's stock return Granger causes the overall market return, or that the market return in turn, Granger causes Microsoft's stock return.
The Toda Yamamoto test, which we have previously discussed, is characterized by the inclusion of an additional lag.
Our statistical analysis did not allow us to reject the null hypothesis. Consequently, we were unable to establish any significant Granger causality operating from Microsoft's performance to the broader market returns, or the other way around.
Finally, we have the VECM, which stands for the error correction model, the very last one that we thoroughly discussed. We've uncovered some truly significant findings from our analysis. It's important to recall that we specifically employed the first difference technique to successfully transform the non-stationary variable into a stationary state. So, we are specifically utilizing the lag change of our x variable, which in this particular instance refers to the lag change in Microsoft's stock return, and that result was indeed quite significant.
So, the fluctuations and changes in Microsoft's stock returns are quite predictable, which means we can effectively utilize their historical lags as a specific form of measuring change. And furthermore, the necessary correction derived from the established long-term relationship is indeed quite significant.
So, we clearly have strong evidence indicating an adjustment towards equilibrium, precisely because the ECT term is significant.
The system also makes corrections for any deviations as time progresses.
So, in this specific scenario, for instance, if a company like Microsoft experiences a significant shift in its financial returns, that particular change is then anticipated to accurately predict its future actions or market behavior.
It's possible there could be a decline during the second period, or perhaps even a more significant increase.
Consequently, the observed shift or modification in the financial return stands out as a truly significant and influential factor. However, despite our efforts, we were unable to discover any evidence suggesting that lag changes occurring within the overall market return possess the capability to effectively forecast future trends or movements.
The variable that we're interested in, which is the Microsoft return. So that should summarize all the methods related to Granger causality. Thank you for listening.